In this video, we will derive a system of equations that will help us find a cubic spline. A cubic spline is a curve that will pass through a given finite set of points. A cubic spline might look something like this. For this curve-fitting method to work, we require the x-coordinates to be all distinct, because after all, we will be looking for a function that will pass through all the given points. And so we have arranged the x-coordinates in increasing order from x sub 0 all the way through x sub n. There should be a total of n plus 1 points, or n plus 1 nodes, and n should be at least equal to 2. Suppose that the cubic spline is given by q of x equals y. Then we impose several conditions on the function q to help us derive the system of equations to help us find the formulation for q. The first and obvious condition is that we require the graph of q to pass through the given points. And so q of x sub 0 should be equal to y sub 0, q of x sub 1 should be equal to y sub 1, and so on. In general, q of x sub k should be equal to y sub k, for k equals 0 through n. Now the cubic spline q is going to be made up of pieces of different functions. So between x sub 0 and x sub 1, we have the piece p sub 0 of x. And between x sub 1 and x sub 2, we have the piece p sub 1 of x, and so on. Altogether, we will have p sub 0 through p sub n minus 1. That is a total of n pieces coming from different functions making up the cubic spline q. The second condition that we impose is continuity. That is, consecutive segments should meet at junction points. For example, p sub 0 of x sub 1 should be the same as p sub 1 of x sub 1. Likewise, p sub 1 of x sub 2 should be the same as p sub 2 of x sub 2, and so on. For continuity, we require that p sub k of x sub k plus 1 equals p sub k plus 1 of x sub k plus 1, for k equals 0 through n minus 2. If it is only continuity that we require, then we only need to find the formulation for the polygonal path that passes through the given points. The third condition that we impose is a smoothness condition. That is, the tangent line should exist at the different nodes. To illustrate this, let's take a look at x sub 1. The left derivative at x sub 1, which is given by p sub 0 prime of x sub 1, should equal p sub 1 prime at x sub 1. And so in general, p sub k prime of x sub k plus 1 should be equal to p sub k plus 1 prime of x sub k plus 1. Again, from k equals 0 through n minus 2. And finally, an extra smoothness condition, this time on the second derivative. The left-hand second derivative at x sub k plus 1 should match the right-hand second derivative at x sub k plus 1. Now for the form of the different p sub k's. Without the smoothness conditions, and with only the continuity condition, we can simply resort to finding the polygonal path passing through all the points. As such, each segment connecting consecutive nodes will be a linear function, and that would be a very easy pre-calculus exercise. There are reasons why we may want to impose these smoothness conditions and not end up with a polygonal path. If, for example, the cubic spline is that for a rail track, such as that for a roller coaster. If the roller coaster track were to be made up of polygonal segments, then the ride could be bumpy if not painful. and thus we have the smoothness conditions. The form that we will take for each of the p sub k's is that of a cubic polynomial, hence the term cubic splines. We can choose p sub 0 of x to be equal to a sub 0 x cubed plus b sub 0 x squared plus c sub 0 x plus d sub 0, and so on for the other polynomials up through p sub n minus 1. P sub k is given by a sub k x cubed plus b sub k x squared plus c sub k x plus d sub k. The constants capital A sub k, capital B sub k, capital C sub k, and capital D sub k are the unknowns that we are trying to solve for. Since we have n different polynomial segments that we had defined, and each polynomial is made up of 4 different unknowns, there are 4 n unknowns in total that we have defined. We will not be using this form of p sub k. We will use an equivalent form for each of the different p sub k's. We will use a form that is based at the left endpoint of each polynomial segment. As an example, let's take p sub 0 of x. The left endpoint is at x equals x sub 0. And so we let p sub 0 of x be equal to lowercase a sub 0 times the quantity x minus x sub 0 cubed plus b sub 0 times the quantity x minus x sub 0 squared plus lowercase c sub 0 times the quantity x minus x sub 0 plus d sub 0. And p sub 1, p sub 2, and so on are defined all similarly. And so in general, p sub k of x is equal to lowercase a sub k times the cube of x minus x sub k plus lowercase b sub k times the square of the quantity x minus x sub k plus lowercase c sub k times the quantity x minus x sub k plus d sub k for k equals 0 through n minus 1. This is just an equivalent form of the original form that we wrote down, which is that using the uppercase a sub k, uppercase b sub k, uppercase c sub k, uppercase d sub k. And now the lowercase letters are the unknowns that we are solving for. To get started finding the system of equations for the unknowns, we plug in the left endpoint for each of the different polynomial segments. If x is replaced by x sub k, note that the only term that will be left will be d sub k. And since p sub k of x sub k is equal to y sub k, d sub k equals y sub k for k equals 0 through n minus 1. This is a total of n equations. Now, even though the last point, x sub n, y sub n, is not a left endpoint, we will still plug in x sub n, but this time to p sub n minus 1, the last polynomial segment. And so p sub n minus 1 of x sub n should be equal to y sub n. This gives us an additional equation. Next, we plug in the right x-coordinate of each polynomial segment. That is, we plug in x sub k plus 1 into p sub k. Now, p sub k of x sub k plus 1 is also equal to p sub k plus 1 of x sub k plus 1, which is equal to y sub k plus 1. But y sub k plus 1 is also equal to d sub k plus 1. And so this string of terms is equal to d sub k plus 1 for k equals 0 through n minus 2. Now we tackle the first set of smoothness equations. For this, we need the derivative of each of the polynomial segments. Differentiating p sub k quickly, we get p sub k prime of x equals 3 times a sub k times the square of x minus x sub k plus 2b sub k times x minus x sub k plus c sub k. Replacing x by x sub k in p sub k prime of x. C sub k is the only term that will be left, and so p sub k prime of x sub k equals c sub k. Replacing x by x sub k plus 1 at the right endpoint of p sub k of x, we get this string of terms. This should match p sub k plus 1 prime at x sub k plus 1. But that is simply c sub k plus 1. And so we have another set of equations. We now take a look at the second derivative equations. The second derivative has something more to do with curvature. Geometrically, curvature means we fit a tangent circle to the curve. But it's not just any tangent circle. Let's look at it this way. Suppose that the cubic spline curve were a stretch of highway. A person going along the circular track, that is the tangent circle, will experience what in layman's terms is referred to as the centrifugal force. The same person traveling along the spline curve at the same speed would experience the same centrifugal force at the point of tangency. P sub k double prime of x is equal to 6 times a sub k times the quantity x minus x sub k, and then plus 2b sub k. Replacing x by x sub k in p sub k double prime, the only term left will be 2 times b sub k. Plugging in x sub k plus 1 for x in p sub k double prime, we get this string of terms. Also, p sub k plus 1 double prime of x sub k plus 1 is equal to 2 times b sub k plus 1. And so we have another set of equations. Let us count the number of equations that we have. We have n plus 1 plus n minus 1 plus n minus 1 plus n minus 1, giving us a total of 4n minus 2 equations. This means we are 2 equations short of the 4n equations that we need in order to have a complete system of equations. For the 2 missing equations, it is up to the user to supply the 2 missing equations. That is, the 2 missing equations are user-defined. What we present here are 2 different types of conditions that will allow us to supply the 2 missing equations. The first condition is that of a natural spline. A natural spline requires that the second derivative values of the cubic spline at the leftmost and the rightmost endpoints be equal to 0. And so we have p sub 0 double prime of x sub 0 equals p sub n minus 1 double prime of x sub n equals 0. P sub 0 double prime of x sub 0 is equal to 2b sub 0. And p sub n minus 1 double prime of x sub n is equal to this string of terms. With the addition of these 2 equations, we now have a complete system of equations, and we should be able to solve for the different unknowns. The second example of a condition is what we refer to as a clamped spline. For a clamped spline, the slopes at the leftmost and rightmost endpoints are defined. Suppose that p sub 0 prime of x sub 0 equals slope 0, and p sub n minus 1 prime at x sub n equals slope sub n. Replacing x by x sub 0 in p sub 0 prime, we get c sub 0 equals slope sub 0. Replacing x by x sub n in p sub n minus 1 prime, we get this string of terms equaling slope sub n. The addition of these two equations completes the set of equations with which we can now solve for the different unknowns a sub k, b sub k, c sub k, d sub k.